All right, so section 3.2 is going to be hopefully a short and friendly section. 3, 3, 3, 4, and 3, 5 may not be so short and friendly, but this is really nothing new. It's called higher derivatives. A higher derivative essentially is just a derivative of a derivative, and you can do 100 derivatives of the same function. Taking a derivative of a derivative is called a second derivative, and then a third, and so forth. So what we've been finding so far is the first derivative of a function, and we haven't had the need to take a derivative of a derivative, but the derivative of the first derivative is called a second derivative, and so forth. So, and the notation is pretty self-explanatory. Well, we've been using the first derivative, so we've been putting 1 prime. If you take a second derivative, you'll put 2 primes to represent second, 3 primes to represent third. I'd have never had a reason to do really even a third derivative. So I don't even know what the symbol for fourth would be. Maybe we'd go into 4 little marks, or we'd do something that's equivalent to a Roman numeral. I'm not sure. So each of these problems are super easy. So for part 2a, to do the first derivative, that's just finding a normal derivative. So a normal derivative is a first derivative. So first, I'm going to go 5 times 3 is 15. Lower the exponent by 1 and get a 15x to the 4th. And then 4 times minus 8 is minus 32. Lower the exponent by 1 and get an x cubed. 3 times 4 is 12. Lower the exponent by 1 and get an x squared. 2 times 5 is 10. Lower the exponent by 1 and get an x. The exponent here is 1 times 3 is 3. Lower the exponent by 1 and get an x to the 0, which is equal to 1. So that derivative of 3x is just 3. And the derivative of 5 is 0. So that's the first derivative. Second derivative is just the derivative of the first derivative. So to do part b, f double prime of x, I'm just going to do the derivative of the first derivative. So 4 times 15 is 60. Lower the exponent by 1 to x cubed. 3 times minus 32 is minus 96. Lower the exponent by 1 to x squared. 12 times 2 is 24. Lower the exponent to an x. Derivative of 10x is just 10. The derivative of the constant 3 is 0. Done with part B. On to part C, doing a third derivative. A third derivative is just the derivative of the second derivative. So take the derivative of this. 3 times 60 is 180. Lower the exponent by 1 to x squared. 2 times minus 96, I'm doing it off screen because apparently I'm afraid I can't do that right now. It's minus 192. Lower the exponent to x to the first. Derivative of 24x is just 24. I didn't do any factoring, and I'm not probably going to do any factoring for my derivatives, because if I factor my first derivative, it makes it harder to find the second derivative. And so I'm just going to leave all these unfactored for now. I'm just going to take some derivatives and be done, and not do any sort of manipulation with the derivatives that I had been doing. When we get into the next section, we're going to use the second derivative to find out some features about the graph of a function. And when I get into that, when I'm actually doing something with the derivative, then factoring it's going to be important. But in this section, I just want to just do the derivatives. All right, so for 3 and 4, we're going to do first, second, and third derivatives. So 4a, first derivative, f prime of x equals, I'll go 4 times negative 2 is negative 8. Lower the exponent to 3. And then 3 times 3 is 9. Lower the exponent to 2. 2 times 4 is 8. Lower the exponent to 1. The derivative of minus 2x is minus 2. The derivative of minus 1 is 0. That's a nice first derivative, unfactored, but completely fine. Second derivative, f double prime of x equals 3 times negative 8 is negative 24. Lower the exponent. 2 times 9 is 18. You get an x to the first. Derivative of 8x is just 8. The derivative of minus 2 is 0. So there's my second derivative. Third derivative, f triple prime. 2 times minus 24 is minus 48. Lower the exponent. Derivative of 18x is 18. The derivative of 8 is 0. That's the whole problem 4. There's not many even problems in this section, so it's just a really nice section. It's going to get worse when we have fractions, or we have e's, but we'll get to those when we get to those. 5 and 6. 6a, first derivative. Negative 3 times 2 is negative 6. Lower the exponent by 1 to negative 4. I'm just going to leave it with a negative exponent. It would be probably okay and maybe better to write negative 6 over x to the 4th. But if I wrote it like that, to do the next derivative, I'd have to write it back like this. So second derivative, negative 4 times negative 6 is positive 24. When I lower the exponent by 1, negative 4 minus 1 is negative 5. And again, it probably would even be better if I wrote it as a fraction, but it's not going to be so important. These problems are only important if you're doing something with the derivative to get the derivative written nicely. Last, third derivative, negative 5 times 24 is negative 120. Lower the exponent by 1 to negative 6. And for each of these, I probably should write the problem with a positive exponent. I'm not sure that much from this section is going to come up on the test. This section is just to make it so the next section wasn't any longer than it's already going to be. So I separated these problems out from section 3.3 because 3.3 is kind of monstrously long, and then throwing an extra half hour into it was too much. Alright, so that's the first 6 problems. The rest of the problems only want me to do 2 derivatives, mainly because maybe the third derivative might be kind of messy, but I don't think this problem is going to be so bad. So first derivative, so 8a, to do the derivative of any e function, you take the derivative of the exponent, multiply it by the function unchanged. The derivative of this exponent is just 2. So the derivative is 2e to the 2x plus 5. When you're doing e's, when you're going to find the second derivative, if there's a number without an x in front of the e function, you don't need to use the product rule, but you can. If there's a number that has an x in front of the e function, you have to use the product rule. So I don't have to use the product rule to do the second derivative for part B, but I could. So if I wanted to for part B, I'd go f double prime of x, and then I could use the product rule because there's multiplication here. So it would be the derivative of 2 times the e to the 2x plus 5 plus the derivative of e to the 2x plus 5 times 2. The reason I don't have to use the product rule is because this derivative is 0. So this would be 0 times e to the 2x plus 5. And then I know the derivative of e to the 2x plus 5 is 2e to the 2x plus 5. So for this derivative, I'm going to write 2e to the 2x plus 5 times that 2. This piece is equal to 0, so I don't need to include it in my work. And for this piece, I simplify by multiplying the 2's together. And so the second derivative for problem 8b is just 4e to the 2x plus 5. For 9 and 10, first derivative, it's an e function, so I multiply the derivative of its exponent times the e function. This exponent, x cubed, has a derivative of 3x squared. So the first derivative is going to be 3x squared times e to the x cubed. Now, when I go to do the second derivative, because to the left of the e there's an x, I have to use the product rule. So to do 10b, the second derivative, I'm going to use the product rule. For the product rule, first I'm going to take the derivative of 3x squared and multiply it by that e to the x cubed. And then I'm going to take the derivative of e to the x cubed and multiply it by the 3x squared. So I'm going to get f double prime of x. The derivative of 3x squared is 6x. I leave the e to the x cubed unchanged. The derivative of the e to the x cubed, you just take the derivative of the exponent, which is 3x squared, multiply it by that e to the x cubed function, and I still have this 3x squared. I'm definitely going to factor out an e to the x cubed to simplify this, because there's a common factor of e to the x cubed. And if I factor out just an e to the x cubed, from this piece I'd have a 6x, and from this piece I'd have a 3x squared times a 3x squared. I'd multiply the 3's, add the exponents on the x's. That would be nice. It probably would be nice if I also factored out a 3x. For these higher order derivatives, I'm not as picky about factoring out the common factor, but you can never go wrong by factoring out a common factor. And I'll tell you on the test what I want you to do. But like I said, the second derivative is something we're going to use, and I don't envision problems on the test saying find the second derivative and don't do anything else. It's what we learn in section 3.3. What you do with the second derivative is going to be what's going to make its way onto the test. But anyways, this is the answer for 10b. 11 and 12 are surprisingly easy. They look like they should be horribly hard, but they're not. LNs are not the worst functions in the world to take derivatives of. So for 12a, when I do f prime of x, because it's a natural log, I form a fraction. In the denominator, I get the argument, which is 3x. And in the numerator, I get the derivative of that argument. The derivative of 3x is just 3. And now I'm going to cancel. And I'm going to get 1 over x. That's part A done. I'm going to move to part B. And I don't really want to use the quotient rule. So I'm going to rewrite this problem so it's not a fraction. I'm going to move the x up to the numerator. It really had an exponent of positive 1. When I move it up to the numerator, I'm going to make its exponent negative 1. And now I can use the power rule. So f double prime of x is going to be negative 1 times 1. And then I'm going to lower negative 1 times 1. And then I'm going to lower the exponent by 1. So the second derivative is going to be negative 1x to the negative 2. And again, it just as habit, it's so easy to do. I'm going to write this as negative 1 over x squared. So best answer definitely for number 1. Best answer for number 2 are those. 14 is another ln. It's not going to be any harder, I don't think. Even though it looks like it might be harder, I don't think it's going to be harder because of the way these things reduce. Alright, so 14, f prime of x. It's an ln, so in the denominator you write the argument. In this case, the argument is x cubed. In the numerator, you take the derivative of that x cubed. The derivative of x cubed is 3x squared. If I go to simplify this, the numerator has 2x's, the denominator has 3x's, can cancel and cancel. And so the best answer for 14a is f prime of x equals 3 over x. When I go to do the second derivative in part B, I'm going to move the x up to the numerator so I could avoid the quotient rule. And now I'm going to write f double prime of x equals negative 1 times 3, and I lower the exponent by 1. So I get f double prime of x equals negative 3x to the negative 2. And the best answer for part B would be f double prime of x equals negative 3 over x squared. All easy problems, and I think we're going to get up to the monster problem right now. I kind of wish I didn't write problems 15, 16, 17, and 18, but I did, so we're just going to deal with them. So, fractions, much less pleasant. So, I need to do the derivative for 16. F prime of x is going to be the denominator, x minus 5, times the derivative of the numerator, which is the derivative of x plus 4, minus the numerator, and the numerator is x plus 4, times the derivative of the denominator, which is x minus 5 squared, all over the denominator squared. That's an unsimplified form of the derivative. I should definitely simplify that quite a bit. The derivative of 4 is 0, the derivative of x is 1, so this just has a derivative of 1. So f prime of x, this is for 16a, is going to be x minus 5 minus, and then, whoa, this should be just the derivative of x minus 5. I got a little over anxious with the square there. The square went down to the denominator. So this x is the numerator times the derivative of the denominator, x plus 4 times the derivative of x minus 5. The derivative of x is 1, the derivative of minus 5 is 0. I'm going to write that derivative of 1 first, times the x plus 4, and then all over the denominator squared. And I could have, with this piece, written times the derivative of 1. It doesn't really matter, because 1 times anything is anything. Now I'm going to drop and get 1 times x minus 5 is x minus 5, minus 1 times x is minus x, minus 1 times 4 is minus 4. In the numerator, the x's cancel, and minus 5 and minus 4 give me a minus 9. So the answer to part A, f prime of x, is going to be negative 9 over x minus 5 squared. So 16a answer. I'm going to be slick and do something I haven't done yet this semester to do my second derivative. Sometimes the quotient rule is okay to use, but when the denominator of your fraction that you need to use the quotient rule for needs the chain rule, I don't want to use the quotient rule. So when I go to do 16b, I start off with the original function f prime of x equals negative 9 over x minus 5 squared. I could go straight into the quotient rule to find this derivative. It's probably better to rewrite this problem so you can avoid the quotient rule. And how I'd rewrite this problem to avoid the quotient rule is I'd move the x to the denominator up to the numerator. And when I do that, I don't have a fraction anymore because I've taken the entire denominator away. But to do that, you have to change the sign of the exponent. Now it's just a chain rule problem. So I'm going to write f double prime of x, multiply the exponent by the coefficient. So I'm going to go negative 2 times negative 9, leave myself some room, and then lower the exponent by 1 to negative 3. And where I left myself some room in the chain rule is to take the derivative of what was inside the parentheses. The derivative of minus 5 is 0. The derivative of positive x is 1. Finish the chain rule. Now I'm going to just clean this up. So for the f double prime of x, second derivative, negative 2 times negative 9 times positive 1 is positive 18. And then I need to get this exponent positive. And I get the exponent positive by creating a fraction and moving the term with the negative exponent down to the denominator of that fraction. That's absolutely the nicest way to take the second derivative of a fraction when the denominator has an exponent in it. If you try to use the quotient rule, it would have got to be a nasty, nasty mess. Alright, so you have problem 15 to do. We just have one more problem in this section each to do. Alright, so 18, I'm going to start off with the quotient rule, because it's an easy enough quotient rule. So I'm going to write 18a, f prime of x equals the denominator, which is x minus 5, times the derivative of the numerator, which is the derivative of 3x, minus the numerator, which is 3x, times the derivative of the denominator, which is the derivative of x minus 5, all over the denominator squared. So I'm going to get f prime of x equals, the derivative of 3x is just 3. I'm going to write that to the left of the parentheses rather than having it to the right of the parentheses. The derivative of x minus 5, because the derivative of 5 is 0 and the derivative of x is 1, is just 1. So I get 3x times 1 for the second piece, all over x minus 5 squared. You can't cancel these x minus 5s because of that part in the numerator. So now I'm going to clean up the numerator. First parentheses, I get 3 times x, which is 3x, 3 times minus 5, which is minus 15. The second, I get minus 3x times 1, which is minus 3x, over x minus 5 squared. The answer to 18a is going to be f prime of x equals minus 15 over x minus 5 squared. If I'm doing part B, I'm going to rewrite part A so it doesn't have that ugly denominator. I'm going to move the x minus 5 squared up to the numerator and make its exponent negative. Makes it so I don't have a fraction anymore. Makes it so I need the chain rule. So now I'm going to do f double prime of x. I'm going to multiply the negative 2 by the negative 15. I'm going to leave myself some room, and then I'm going to take the x minus 5 and lower its exponent to negative 3. Where I left myself some room, I do the derivative of the inside of the parentheses. The derivative of negative 5 is 0. The derivative of x is 1. So that's my derivative. Now I just clean it up. I multiply all of these and get positive 30. And I move this down to a denominator to get its exponent to be positive. And that's the whole answer to 18b. And that's the entire section. Again, I don't think this section's going to pop up really heavily on the test. It's going to pop up indirectly because as we do the problems in the next few sections, you're going to need to be able to take a second derivative. And I don't think we'll ever need to be to take a third derivative. I don't remember ever needing a third derivative in another class. So, but the second derivative is something, it's an important skill to have later in the chapter.